Okay, today we're going to start the second part of the course. Up until this point, we've been doing what's called differential calculus, which means that we've been concentrating on derivatives. Now we're going to switch over to a different part of calculus called integral calculus. Okay, and I'm going to draw something here.
I guess everybody would just do like 2 slides.
Let's draw that symbol and then put a function like 3x squared plus 4x plus 5. Okay, and then this dx. Okay, now this is what we call an indefinite integral. Okay, and here's how you read it. I'll say the words that come out of your mouth as you move your eyes across those symbols. Okay, so that part right there, you say the integral of and then let's use a different color. This part's pretty self-explanatory. 3x squared plus 4x plus 5. Okay, and then when you get to the dx, you say with respect to x. Okay, the integral of 3x squared plus 4x plus 5 with respect to x. That's how you read that. Okay, what is it? It's called an indefinite integral. All right, now we've talked about things so far that are just words. Now let's talk about some math. What do you do when you see that symbol? What does it ask you to do? Okay, so I said it's called an indefinite integral, but what does it mean? Okay, here's what it means. This is the antiderivative of 3x squared plus 4x plus 5. Look at that word there, antiderivative. What does it mean? Okay, you can say it a few different ways. You can say it's the function whose derivative is 3x squared plus 4x plus 5. Okay, that's one way to say it. Let me write that one down. The function whose derivative is 3x squared plus 4x plus 5. Okay, another way to say it, or another way to think about it, is to say this. If you were doing the derivative of something and you got 3x squared plus 4x plus 5 as an answer, then what is the function you would have started with? Okay, another way to think about it is to say you're doing derivatives backwards. Okay, so there's lots of ways to think about it. So now that we've said what it is, let's see if we can figure out the answer. Let me move this over so we have room. So what should that equal? Let's think about that. What function has a derivative of 3x squared plus 4x plus 5. Well, let's just take it one part at a time. Whose derivative is 3x squared? Do you agree that that would be x cubed? Because the derivative of x cubed is 3x squared. Okay. Whose derivative is 4x? Do you agree that that would be 2x squared? Because the derivative of 2x squared is 4x, right? Whose derivative is 5? Do you agree that that would be 5x? Because the derivative of 5x is 5. Do you see what I'm doing after I write down the answer? I'm checking it to see if I'm right. You can always check an answer for an integral by just doing the derivative of your answer and seeing if it equals this. By the way, the function inside an integral is called an integrand. Okay, so when you calculate an integral, you're basically just asking your mind to think through a derivative in the backwards direction. And when you write down your answer, you can always check your answer and see if it's right by just doing the derivative of your answer and seeing if you get the integrand. If so, then you have the right answer for the integral. You see how that works? Okay, now there's a bit more to this. I think that that's not the only right answer, because let's go ahead and write this down here. The derivative of x cubed plus 2x squared plus 5, x is 3x squared plus 4x plus 5. I'm going to erase this green sentence here. It's kind of in our way. Okay, but isn't there other functions that have that same derivative? For instance, couldn't I also say the derivative of of x cubed plus 2x squared plus 5x plus 7 is 3x squared plus 4x plus 5? Isn't that also true? Because the derivative of x cubed is 3x squared, the derivative of 2x squared is 4x, the derivative of 5x is 5, and the derivative of 7 is 0. Let me write down another sentence. The derivative of x cubed plus, hang on a second, plus 2x squared plus 5x plus 23 is 3x squared plus 4x plus 5. Correct? Do you see what's happening there? I could put any constant here at the end, couldn't I? And I would still have a function whose derivative is this. So any of these would be a correct answer for that integral up there. So what I have here, when I have an indefinite integral, we get what we call an answer, but the reality is it's not one answer, it's actually infinitely many possible answers. And for this one, it would be x cubed plus 2x squared plus 5x plus any constant. So I write at the end plus c. And my explanation in gray, where it says this is the antiderivative of 3x squared plus 4x plus 5. Okay, that's okay. I did have something else written there also, didn't I? And it was in green. Let's put that back. There was also written here the function whose derivative is 3x squared plus 4x plus 5. Now you see the language there is singular, isn't it? But in reality, we don't get a single answer. We actually get infinitely many answers. I write only one thing. I write x cubed plus 2x squared plus 5x plus c. But that takes into account infinitely many different answers because the constant c at the end could be any number. So the reality is, what I have written there in green is the quantity there is wrong. It says the function. That's singular. It should really say the functions, plural. And then instead of saying whose derivative is 3x squared plus 4x plus 5, it should really say the functions, plural, whose derivatives are 3x squared plus 4x plus 5. You see, it's plural. Okay? Do I need to make any grammatical corrections to the sentence that's written in gray? This is the antiderivative of 3x squared plus 4x plus 5. It's not wrong the way it's written. You just need to understand that when we say the antiderivative of something, that is not a singular thing. The antiderivative of a function is infinitely many different functions. Okay, so it's not wrong. However, to avoid any confusion, it is a good idea if I were to put in after the word the, to put in the word general. Instead of just saying the antiderivative, it's a good idea if I said the general antiderivative. Meaning, look at these 3 examples down there, and I think you understand that I could have written 300 examples if I wanted to, right? By just picking a different number to put at the end. Okay? So what I'm trying to say, I think you probably get the idea, but I'm just trying to wrap it up here, is that there's 3 different answers here, 3 different functions, okay? But they all have the same general form. Did you hear the word general there? They all have the same general form, and that's the form x cubed plus 2x squared plus 5x plus a constant. That is the general form of every antiderivative of that function. So we call that the general antiderivative. And that's how we write the answer to an integral. Okay? Now, the good thing about this is, technically, you're not learning any new math. You're just learning a few new words. That's all. There's absolutely no new mathematics at all. Because all we're really doing is derivatives, except we're just doing them backwards. Okay? So you already know lots and lots and lots of integrals. Okay? Let's go through here. Let's write down a whole bunch of integrals that you already know. For every derivative that you know, you also know an integral. Okay? Let me show you what I mean. Let's look at the function x to the n. What is the derivative of that with respect to x? Well, you know that it's n times x to the n minus 1, right? That's how you do the derivative of x to the n. You bring the exponent down and put it in front, and you subtract 1 from the exponent, right? So, in that case, what would be the integral of x to the n with respect to x? So, let's think about this. When you're doing the derivative, you subtract 1 from the exponent. So that means when you're doing the integral, you must add 1 to the exponent. You agree with that? When you do the derivative, you subtract 1 from the exponent. That means when you do the integral, you should add 1 to the exponent, because the integration is just backwards differentiation. Okay? Next question. What's the number that goes in front? So let's think about that. When you do the derivative, you multiply by the exponent. Right? You agree with that? You see, look over here on the left. When we did the derivative, we multiplied times n, which was the exponent. Okay? So therefore, when you do the integral, you should divide by the exponent. So that brings up two possibilities here. Maybe I should put 1 over n, because n is that exponent there. Or is it this exponent that I should be using? Should I be putting n plus 1 down there? Okay, well, let's just check, because I agree that it's not obvious which one. So, quick review here. Quick review. Where did that come from? When you do the derivative, you subtract 1 from the exponent. Therefore, when you do the integral, you should do the backwards, which is add 1 to the exponent. Okay, so I hope that makes sense. And then the other thing that I hope makes sense is, when you do the derivative, you also multiply times the exponent. Yes, that's right, sorry, times the exponent. So therefore, when we do the integral, we should divide by the exponent. The only question is it that exponent I divide by, or that one? Should this be an n down here, or should it be an n plus 1? Okay? So let's just check. It's one of those two. Should it be 1 over n, x to the n plus 1? Or should it be 1 over n plus 1, x to the n plus 1? How do you check? You do the derivative and see which one has this derivative. So let's just check. What's the derivative of that? It would be n plus 1 over n times x to the n, right? What's the derivative of this? It would be n plus 1 over n plus 1 x to the n. And these would cancel. And we get x to the n, which is here. So that means this is the correct thing that we should be writing. And so there, what is written in black up there is the correct answer. Just missing one thing at the end. What is it I'm missing at the end? Plus a constant. And I'm not saying that you pick a constant to put there. I mean you literally write plus c, where c stands for any constant. Okay? So you already knew that derivative. Now you know this integral. Okay, let's go through some more. What are some other derivatives that you learned in this class so far? You learned that the derivative of sine equals cosine, right? That means that you also know the integral of cosine equals sine plus a constant. Okay, what's another derivative that you know? You know the derivative of cosine is negative sine that means the integral of negative sine equals cosine. Plus c. Now I don't want to leave it like that. I could, there's nothing wrong with it, but there's a different way I would rather write it. I would rather write down what's the integral of sine. So here's what we're going to do. We're going to take that negative. Doesn't that mean, when I say negative sine, doesn't that mean -1 times sine? What we're going to do with that -1 is called factoring it out of the integral. I'm going to take it and put it out here. And now we are going to cancel it out by dividing both sides by -1. That'll cancel that out. So we have the integral of sine on the left. And on the right, we have cosine divided by -1. Isn't cosine divided by -1 just negative cosine? That's the way I would like to have it written. So remember your derivatives. The derivative of sine is cosine. The derivative of cosine is negative sine. Now you know two integrals. The integral of cosine is sine, and the integral of sine is negative cosine. Okay? Now that business I did about taking the -1 and moving it to the front of the integral, okay, I should show you that that's okay. And I will in a few minutes. Okay? Let's just wait a few minutes for that. Let's write down a few more derivatives that you already know, and then write down the integrals that go with them. Okay? So the derivatives of sine and cosine, I certainly hope you have memorized. But there's other trig functions, right, like tangent and cotangent and secant and all of those that we technically know the derivatives of, although you might not have them memorized. But let's write them down anyways. We know that the derivative of tangent is secant squared. That means the integral of secant squared is tangent. And not everybody remembers that, but you really should. I would like you to remember that one. If you take Calculus 2, it's going to come up over and over and over again. You're going to need to have it memorized. Okay? We know that the derivative of cotangent, you might not remember, and that's okay, but I'm just reminding you that we have written it down once before. And the answer was, for the derivative of cotangent, was negative cosecant squared. That means that the integral, here let me just move this down a little so we're not getting too jumbled up. Okay, that means the integral of negative cosecant squared is cotangent. And now I'm going to do the same thing with that negative sign. I'm going to factor it out front. And then I'm going to move it to the other side, just like we did with the sine earlier. Okay, the integral of cosecant squared is negative cotangent. The derivative of secant was secant times tangent. So that means the integral of secant times tangent is secant. You see, the point I'm trying to make is that every derivative that you learned, you also learned an integral. You just didn't know those words yet. Okay, another one. The derivative of cosecant is negative cosecant times cotangent. That means the integral of, what do you think I'm going to write here? Cosecant times cotangent equals, what do you think? Negative cosecant. Okay, let's do two more. We already know the derivative of e to the x is itself. That means the integral of e to the x is itself. And one more. I don't know if you remember or not, because we did not make a big deal out of it at the time. But we did look at it at least once. The derivative of the natural log of the absolute value of x equals 1 over x. That means the integral of 1 over x equals natural log of the absolute value of x. Now that last one there, especially the absolute value part, you don't need to worry about that because we're going to teach you that one again in Calculus 2. Okay, so don't worry about that last one really. But definitely, here are the ones that you should be able to do
Yeah.
off the top of your head. Ones like that. Sine and cosine. You should really be able to do tangent off the top of your head too. You're going to need to memorize that one for Calc 2 especially. And e to the x. Okay. This one here will come up a lot in Calc 2 as well, believe it or not. But definitely the 5 that I have check marks by, you should be able to do those derivatives and those integrals by memory. Okay? Okay, now there are a few rules about integrals that I want to show you, just like there were some rules about derivatives. Remember the product rule and the sum rule and things like that? So I want to go over some rules for integrals as well. Okay, and we're going to get these rules by just looking at derivatives. Okay, so I want you to remember this rule about derivatives. If you have f of x times a constant, I'm going to use lowercase c, all right, not capital C. I'll use lowercase c. All right, you remember this, I'm sure, that when you do the derivative of that, you get c times f prime, right? In other words, you can factor a constant out of a derivative. The derivative of c times f equals c times the derivative of f. That's what allows me to factor a constant out of an integral. And that's what I was doing earlier with those negative ones. Okay? Because we're allowed to factor a constant out of a derivative, that's why I'm allowed to factor a constant out of an integral, because an integral is just a backwards derivative. Okay? One other rule about derivatives was the derivative of f of x plus or minus g of x equals the derivative of f plus or minus the derivative of g. That means the integral of f plus g equals, plus or minus actually, equals the integral of f plus or minus the integral of g. Okay? I just want to point out to you, notice that every integral ends with a d and then the variable. Just like every sentence ends with a period. If you leave that off, that's called a differential. If you leave that off, then you don't have it written correctly, okay? Now we can put both of these rules together, which people often do in textbooks. They put them together and they write this. The integral of, I'm going to write two constants this time. Let's call the constants a and b, okay? So the integral of a times f of x plus b times g of x can be broken up into a times the integral of f plus b times the integral of g. And that also works if it were minus, by the way. So this one rule right here is just a combination of these two rules put together and written as one. Okay? And that has a name. That's called linearity of the integral. So that's a very important rule, okay? Now I want to point out two things that are not true. This is very, very important. The integral of f of x times g of x is absolutely not the integral of f times the integral of g. And the reason why is because the derivative of f times g is not the derivative of f times the derivative of g. The product rule was much more complicated than that. So the integral of products is much more complicated than that. Same thing with division. The integral of f of x divided by g of x is not equal to the integral of f divided by the integral of g. The quotient rule for derivatives was much more complicated, and therefore the integrals of quotients are much more complicated. Okay? We will handle things like that in Calc 2. Some of them are just very straightforward. Like if I asked you to calculate the integral of 2x times x squared, you could do that because that's just 2x cubed. Okay? But if I asked you to do the integral of something like x times sine of x, you would not be able to do that one yet. We'll handle that in Calc 2. Okay, something else to cover. The integral of a constant is always going to equal that constant times x plus capital C. Let's not forget that. Because the derivative of a constant times x is just the constant. So the integral of a constant is that constant times x. Which means specifically the integral of 1 equals x. Okay? Here's another one that's handy to remember. The integral of nothing is a constant, because the integral of a constant is 0. The derivative of a constant is 0. So the integral of 0 is a constant. Any constant. Okay? So let's just, now that we've covered all of the rules and everything, let's just practice some problems here. Okay, let's integrate 10x squared minus 2. It takes a little bit of getting used to, because now you're switching gears and you're doing the derivative backwards, right? So that takes a little bit of mental flexibility, but this will become second nature for you, okay? Just remember the rules that we wrote down earlier. So when I integrate 10x squared, let me walk you through it. Here's how I do it, okay? I write down the 10. I write down the x and add 1 to the exponent. And then I put 1 over that new exponent in front. That's exactly the rule that we wrote down earlier. Up here. Right there. Okay? Then I have the integrand minus 2. So when I integrate, that becomes minus 2x, correct? And that's the end. We put plus c and we're finished. So remember this part here. Okay, remember what I said. I copy the constant. I add 1 to the exponent. And then I multiply times 1 over that new exponent. Okay? Let's do a new one. Let's integrate 5 minus 2/3 x squared plus 3/4 x cubed. Okay? So the integral of 5 is 5x. Then I have minus 2/3 x cubed, so I write minus 2/3. Sorry, it was x squared. But now when I integrate, it becomes x cubed. And then I multiply by 1 over that new exponent. So that's going to be negative 2/9 x cubed. Okay, then we have plus 3/4. It's going to be now x to the 4th, and I'm going to get 1 over 4 in front, so I have plus 3/16 x to the 4th. And then I put my plus c, and then I'm done. How do I check my answer? Just do the derivative and see if it gets you back to this. Okay? Let's integrate the square root of x to the 7th. Well, that's actually nothing new. Let's just write that as x to the power 7/2. So when I integrate, it becomes x to the power 9/2. And then I put 1 over 9/2 in front, which means I put 2/9 in front. And there's my answer. How about x cubed minus 7x over x squared? Now, I said that we're going to learn how to integrate quotients later, but some of them we can do now. This one is actually not difficult. It's actually very easy. You just have to rewrite that as x to the power of 3 minus a half, which is 5/2, minus 7x to the power 1/2. That's just algebra. You agree that this is correct? So my answer will be x to the 7/2 with a 2/7 in front minus 7x to the 3/2 with a 2/3 in front. So that's 2/7 x to the 7/2 minus 14/3 x to the 3/2. Okay, there's really not much more to it than that. At this point, integration can be difficult, and we spend almost the entire semester of Calc 2 learning how to do harder integrals. Okay, but basic integrals, there's not much more to it than this. You're just doing the derivative backwards. That's all. Okay. Let's do one more problem and then we'll be finished. Something like this. Find f of t given that its second derivative is cosine and f prime of 0 equals 3 and f of 0 equals 5. This is what we call an initial value problem. And let me show you how to answer something like that. Okay, you start with this here. Okay, the second derivative is cosine. Now, I want you to think about this. If I were to integrate the second derivative, my variable, notice here, is t, so I put at the end here dt. Okay, remember that an integral is just backwards derivative. So the integral of the second derivative should take me back to the first derivative. So f prime of t is the integral of f double prime. Okay, and they told me f double prime is cosine. So that's the integral of cosine of t. What's the integral of cosine? Remember, it is sine. So f prime of t equals sine of t plus some constant. Now, you use this information to figure out what constant must go here. Because I'm looking for a specific function here, not infinitely many functions. If this was all they gave us, just give me a second here. Let's take this part. Oops. Let's take these two parts. Let's take them away for a minute. If that was the whole question, then this would be the whole answer. And the answer would not be one function. Oh, actually, sorry, that's only f prime, so I would still have to go backwards one more time, wouldn't I? Let's go ahead and do that. Let's finish that. Okay, so if this was the whole entire question, then I integrate f double prime to find f prime, and then I integrate f prime to find f. So we would integrate sine of t plus a constant, and I would get negative cosine of t plus capital C times t, right? The integral of c would be c times t, plus a new constant. We'll just call it d. And that would be my answer. Okay? But that wasn't the whole question, was it? They actually gave us more information. They told us these two additional pieces of information. So what we do is we use that information to get one single answer instead of infinitely many answers. Okay, and what I do, let me erase this second line here, because before I even got to that, I would do this. I would use that information right there. I know that f prime of t equals sine of t plus a constant, and I also know that f prime of 0 equals 3. So let's plug in 0 to our answer, and I write f prime of 0 equals, so they give me the value. They say it's 3. Let's put that on this side. But I can also calculate the value, and I would get sine of 0 plus c. What's the sine of 0? It's 0, so that's 0 plus c, which is c. You see what I have here? That capital C equals 3. So I have f prime equals sine of t plus 3. Okay? Now I integrate f prime to get f. F of t is the integral of f prime of t. So that's the integral of sine of t plus 3 which is negative cosine of t plus 3t plus a constant. I'll use d this time. Then I use this piece of information to find d. Okay, we look at f of 0. I know what f of 0 is two different ways. They told me it's 5, and I can calculate it to be negative cosine of 0 plus 3 times 0 plus d, which would be what? Negative 1 plus d. So 5 equals negative 1 plus d. What is d? D would have to be 6. So my final answer then is f of t equals negative cosine of t plus 3t plus 6. And that's my answer. Okay? That's how you do what's called an initial value problem. Okay, that's it for today.